got to go and dig those holes.
Man, I'm tired.
With broken hands and withered souls, emancipated from all you know. You got to go and dig those holes.
Man, you slow, dude. Beats, man. Oh, that's what we're doing. We're singing. Y'all know nothing about this. Watch me. Watch me. Come on, Ed. Come on, Ed. Prove yourself.
Dig it all, dig it. Dig it all, dig it all, dig it. Dig it all.
Two suits, two tokens in hand. I got no respect cause I'm the new man. Got my shovel, shoes full of sand.
Alright, welcome to section 3.1. We're going to continue talking about the domain and discontinuities in this unit, but in this particular section we're going to take a look at how we can find the domain algebraically. So that means we're going to be doing some math in this lesson and not necessarily just looking at a graph and analyzing the domain. By the way, the little song at the beginning was from the movie Holes. I don't know if you've seen it before. It's the Disney movie with Shia LaBeouf in it before his Transformer days. But we're also, since we're going to be talking about the discontinuities today, more specifically that removable type, which we can refer to as a hole, I thought it was kind of an appropriate song. Alright, so anyway, we're going to be taking a look at equations today. That's what I mean by an algebraic approach, instead of looking at a graph. But let's just recall some information from the Unit 2 that's going to help us today in this Unit 3, Section 1. So from Unit 2, we talked about how the domain refers to all possible x values for a function. And graphically speaking, we use the idea of how far left can our graph go, and as we move across it, how far right can our graph go. So we just take a look at this picture. Normally we would assume that we have little arrows on these, so I'll go ahead and draw those in. And graphically speaking, since this arrow is going to continue as far left as it wants to, my domain can start at negative infinity. But as we move across our graph, oh, I don't want to move that. As we move across our graph, notice how when I move across it, I am continually touching at least some piece of it. Even here at -2, where there seems to be some type of jump discontinuity, I can still touch my graph at this closed circle, but not that open one. So since I can continue to touch it, I'm going to continue to move across my graph. And I'm still touching it, I have another, looks like a jump discontinuity right here at 1, but notice how I can still touch a piece of my graph. I have a value towards the bottom right there at -2 that allows me to touch my graph. Now you could also consider this a removable discontinuity because we have this hole going on in our smooth curve. So this would actually classify as two different types of discontinuities. But as I continue to move across my graph, I can continually touch it till the very end, because this piece is going to continue down and right forever and ever and ever. So since it can go as far right as it wants, we can go all the way to positive infinity. So if we can include every single number going as far left and as far right as we could go, we can say that our domain is all real numbers. Okay, so remember the domain is referring to the x values. Any single x value you want to put into this function, you are going to get a point on your graph. Now these types of discontinuities, we're going to continue talking about them today. Again, we had some type of jump discontinuity right here. That would be a removable type. We would say that is at, or non-removable rather, at -2. But you could also classify this item right here as a jump because you're jumping between values. But you can also consider it a removable because we specifically have that hole. I would consider it more a removable type than a non-removable, or besides that non-removable jump, because it is specifically a hole. Okay, jumps normally look like this, where you have one piece of your graph and then you jump to another one and you continue from that point. Notice how this one we jump down, but we do not continue from this piece. So I would consider this one more of a removable type than that non-removable jump, but I can see how some of us, or even I sometimes, would look at that and consider it a jump discontinuity. Alright, so little things to remember as we go through this lesson today. Now let's try to dive into our domain and how we find it with algebra. Okay, so there's two things we're specifically going to focus on in this lesson, and those two things are fractions and square roots. Okay, so we're going to start off by looking at fractions, and let's try to remember what is special about fractions. Okay, when you're dealing with a fraction, just like our little example here, the denominator can't be what? Okay, so the denominator of a fraction can be any single number you can think of, except what number? Hopefully we remember that that is the number 0. Okay, you can never, ever, ever divide by 0. If I even try to show you that on your calculator, maybe we'll do 8 divided by 0. It is not going to work. Your calculator is even going to tell you you cannot divide by 0. So that's something that we want to focus on because that's something very special about our fractions. Okay, the denominator cannot be 0. Meaning, if we have an x value in our denominator, that x value might have some type of a restriction on it, meaning it cannot be a certain value. So if x cannot be a certain value, that means it is not in our domain. So if we take a look at our fraction in this case, since we know the denominator cannot be 0, let's actually write that fact mathematically or algebraically. Our denominator in this case is x plus 1, and we know it cannot be 0. So in that, or algebraically, that means we cannot equal 0. So we're going through this process to help us find the domain of this function. So this is the only restriction we have since we're dealing with a fraction. We know the denominator cannot be 0. But if we solve for x to figure out that one specific value that does not work, we can subtract 1 from both sides, and x cannot equal -1. Okay, so this is a domain value that does not work, meaning that it can be any other number you can think of. You can put in any other number you want for x and it will work, but the moment you put in -1, it will not. So we would say our domain value for this particular function is any number you want except x cannot equal -1. Alright, so moving on to the next example, we have our little thinker guy here, which means you can pause the video and try to do this one on your own if you want to, but I'm going to go ahead and do it do it along with you just because it can be a little tricky. Since we're dealing with a fraction and we want to try to figure out what is our domain, what x values work or don't work, we know that for fractions our denominator cannot be 0. So that's the only piece we want to focus on because that's what's really special about fractions. Okay, the denominator cannot be 0. So if this is our denominator, we know it cannot be 0. So we're going to write that algebraically by saying it cannot equal 0. Now, if we look back at the last example, it was really easy for us to solve for x because all we had to do was subtract 1 on both sides. But looking at this one, we have multiple x's happening in here, which means we might have to do a few more steps to help us figure out what can x not be. And since we're dealing with multiple x's here, it might be a good idea for us to factor. Try to get those x's individually, that way we can look at each one separately. So if we think about factoring in this example, we can probably take out an x because they all have an x in common. So we're left with an x squared plus 5x plus 6. And again, it still does not equal 0 because we're specifically looking at our denominator. If we continue to factor, because we can factor this, this quantity inside the parentheses, two numbers that multiply to 6 but add to 5, would be a +3 and a +2. And again, it cannot equal 0. So now that we have three pieces here, we have the x out front, we have this x plus 3 quantity, and this x plus 2 quantity, we can figure out which values for x's are not going to work. So either our first part does not equal 0, according to our equation here, it does not equal 0. Our second piece might not equal 0. And our third piece might not equal 0. So just like in our factoring section, to figure out what x is, we're looking at each piece individually. Well, this one right here is already solved for x. So x cannot equal 0. That's definitely a number that is not in our domain. If we were to solve for the other piece by subtracting 3 over, we would get another value that x cannot be, which is -3. And for the last one, if we subtract 2 over, another domain value that will not work is -2. Alright, so we'll say as our final domain, every single x value that you can think of to plug into your equation will work, except x cannot equal -3, -2, and 0. Those are the 3 numbers that you cannot pick, because the moment you'll put them in, you will be dividing by 0. Right? And you know that you can't do that in a fraction. So any single number you can think of will work, except for these 3 values. Alright, looking at our last and final example for our fractions, if we're trying to find the domain value, we're trying to figure out what number does not work in the bottom. And our denominator in this case is 2, and because it's a fraction, we know our denominator cannot equal 0. Now this one's tricky because notice how we do not have an x value in the denominator like we did in the other examples. And if you notice what you have written here as your equation, or 2 cannot equal 0, this is a true statement. Okay, it actually makes sense. So in the other examples, notice how we had restrictions on x. X cannot equal 0, x cannot equal -3, x cannot equal -2. In the first one, x cannot equal -1. This one, we don't really have any restrictions. So maybe we'll write that down. No restrictions on x. Okay, that's our variable, that's our domain. So this is telling us it's always going to work. Okay, notice how we have a true statement. So if it's always going to work, there's no restrictions on our variable. That means you can put in whatever you want and it'll always work. You're always going to get something true, something that makes sense. So if there aren't any restrictions on our domain, on our x value, then we would have a domain of all real numbers. Absolutely anything you can think of will work for this equation. Alright, so now let's move on to some square roots that we have here. And an even root, like a square root, for example, or maybe we'll be dealing with fourth roots. I'm not really sure if I want to do that to you guys just yet. But an even root, like a square root, cannot be negative. Okay, you cannot take the square root of a negative number. You're actually going to get an imaginary number. And we're going to look at those actually later in this section. I think you have some examples of that in your skills practice towards the end of the lesson. But an even root cannot be negative. You cannot take the square root of a negative number. If I were to show you that again on your calculator, if we tried to take the square root of maybe -4, okay, some of you might be tempted to say that it's -2, because the square root of 4 is 2, but notice how on your calculator you're going to get a non-real answer. Okay, it is not a real number, it's actually an imaginary number. So we cannot take a square root of a negative number. And remember, negative numbers, like -1, -2, -3, okay, those values aren't going to work. So for our domain, we want to focus on x values that are greater than 0, because numbers greater than 0 are positive. Okay, we don't want them to be negative, but they can also equal 0, because 0 itself is not negative. Okay, it's not positive either, it's kind of a neutral number, but we want to try to find domain values that are greater than or equal to 0. So this is going to be a big idea, just like when we looked at fractions, we cannot equal 0 in our denominator. When we're looking at roots, we want our domain to be greater than or equal to 0. So taking a look at this example, we cannot take the square root of a negative number. So this radicand, which is the inside stuff, I guess is what you could say, cannot be 0, or cannot be negative, rather. So the inside quantity would have to be greater than or equal to 0. Okay, because this quantity cannot be negative. You cannot take the square root of a negative number. So if we start to solve for x by moving some things around, we can subtract 3 on both sides, and dividing by 7, would give us -3/7. Okay, so this is telling us what our domain actually is. We can put in any x value we want as long as it's greater than or equal to -3/7. Okay, so notice how your x values can be negative, but the moment you plug them in and simplify, your overall answer inside the square root cannot be negative. So our domain for this example, we can put in any x value we want as long as it's greater than or equal to -3/7. Now, if I were to try to give an example of this, okay, I'm going to pick an x value maybe of, I don't know, we'll say 0. Okay, because 0 is greater than or equal to this -3/7. So if I put in 0, I want to get the square root of 7 times 0, which is 0, plus 3 would give us 3. Okay, I can actually do the square root of 3 because this number is not negative. But maybe I wanted to try -1, which is definitely not greater than or equal to this -3/7. If I put in -1, I want to get the square root of -7 plus 3. Which is actually the square root of -4, which we did on our calculator, and it would not work, okay? So even though this answer is negative, okay, we're concerned about the overall number inside, okay? The overall number cannot be negative. So in this case, domain values greater than or equal to -3/7 would work. Alright, moving on to our next one. This one's actually kind of tricky because we're dealing with a square root and a fraction all in one. Okay, so we got to use both of those ideas about the denominator cannot equal 0 and square roots have to be greater than or equal to 0. So looking at this square root right here, I know that the radicand, the inside quantity, has to be greater than or equal to 0. Okay, so that's just what the square root is telling us. But notice how it is in the denominator. Okay, so it is in the bottom of a fraction, meaning that we cannot equal 0. So taking a look at our inequality we have right here, we know it's set up correctly, but we might have to change something because it cannot equal 0. So we're going to get rid of the little equal part down here, because it is in the denominator of a fraction. Okay, so we're looking at the square root to help us to get the setup, but since it's in the denominator, you cannot equal 0, so we cannot have that bar underneath our inequality. So if we started to solve for our domain, we want to get x all by itself, we can subtract 5 on both sides, and then dividing by -1 would give us x is now greater than, okay, we got to remember our rules about inequalities. When you multiply or divide by a negative number, you got to switch that sign. So instead of being greater than, it's now going to switch to a less than. -5 divided by -1 would give us a +5. Okay, so our domain values for this particular equation would have to be x values that are less than 5. You can put in 4, you can put in 3, you can put in -2. Okay, you can put in any x values you want as long as they are less than 5. Alright, moving on to our last example of a square root. This one is kind of like the mother of all problems because not only do we have a fraction again, but we also have a square root. So we're going to have to use both ideas of the denominator not being equal to 0 and square roots having to be greater than or equal to 0 to help us with this particular example. So let's just take a look at our denominator. Okay, that piece is telling us that x plus 5 times x minus 5 cannot equal 0. Okay, that's what this is telling us. But we also have a square root that we have to worry about, and we know the inside radicand has to be greater than or equal to 0. Now in this particular case, I need that equal part because it is not in the denominator. Okay, since it's in the numerator this time, the numerator can actually be 0. I need that equal part. So it's just when your square root's in the denominator that we need to get rid of that because the denominator cannot equal 0. So this time we actually have two pieces we need to solve in order to help us to find our domain. So if we look at the left side, we either have our first quantity that doesn't equal 0, or we have our second quantity that doesn't equal 0. If we were to solve the first one by subtracting 5, we would have an x value that cannot equal -5. And if we were to solve the second one, we would get an x value that cannot equal +5. Okay, so here are two restrictions on our domain. We have two numbers that x cannot be, but we still have this other piece to help us out. So let's solve this one, adding 6 to both sides, and then dividing by 2 would give us a solution of x's that are greater than or equal to 3. So our overall domain, since we had two pieces we had to kind of solve, are our answers from those two pieces. So we need x values that are greater than or equal to 3, but we also have some particular restrictions on certain values. X cannot equal -5 or +5. So our overall domain is the combination of both of these answers, because both of these answers came from our entire equation. We have to look at each piece separately and then combine them together to get our overall domain. Alright, so now that we know how to find the domain of a function algebraically, we're going to talk about those different discontinuities that can happen on our graph. So when we're finding those x values that do not work, okay, we cannot put them into our equation. Since they're not a part of our domain, that means we have a discontinuity. Okay, we need to actually pick up our pencil at that point on our graph because we do not have an x value there. So we're going to go through the same process with fractions and square roots like we've been talking about, but this time identify exactly which type of discontinuity is happening at that x value. Do we have a removable whole, or do we have a non-removable infinite asymptote that's happening at that particular point? So we're going to discuss what can actually happen at those discontinuous x values that do not work. So the first part we're going to focus on right here are those vertical asymptotes. Those are the dotted lines, the infinite discontinuities that we talked about, and they were the if I can write it neatly in here, non-removable. Okay, so those were the non-removable, more specifically infinite discontinuities. We're going to find those vertical asymptotes. Now if you take a look at number 7 here, it is the exact same problem we did on number 1 on your paper, if you want to reference that. And the domain value that we found was that x cannot equal -1. Okay, when we set that denominator equal to 0 and we solved, this was the particular x value that did not work. Okay, so if we look at our graph, maybe we'll graph it to see what's going on here. Go to our y equals, and you gotta be careful when you're typing in a fraction because we want to take the entire top, which would be x minus 5, and divide it by the entire bottom, x plus 1. So we need to put it in parentheses to denote the entire top being divided by the entire bottom. Oops, I didn't mean to do that. Here we go. Now let's hit graph. Okay, so my window right here is set to -5 and 5, and we're counting by ones, but maybe I'll change it just a little bit. We'll zoom out to see what's actually happening here. I'm now going to go to -10s instead of -5s. There we go. And notice how, okay, your calculator is not going to draw in those dotted lines, but we can kind of imagine where it might be. Notice right here we said the x value that does not work is -1. So on our x-axis, if we look at -1, that's where we can kind of imagine that vertical asymptote occurring. Okay, we can actually think about a dotted line going through that point. So this particular x value right here is a discontinuous point, and according to our graph, we can label it as a vertical asymptote. Okay, because that's where it is a non-removable infinite, we have that asymptote going on, that non-removable infinite discontinuity. So graphing your equation might help you identify what exactly is going on at that point. We're eventually going to talk about a shortcut way towards the end of this lesson to figure out what this actually is, but you can always check graphically what's going on at this x value that does not work. Alright, so if we take a look at number 8, again, this is the exact same equation we had from the second example, if you want to take a look at it on your paper. And we found the domain to be every single number you can think of, except x cannot equal -3, -2, and 0. This is what we had to factor in order to help us to figure out those x values. So again, we want to figure out what type of discontinuity is occurring at each one of these values. So again, graphically, maybe we'll check it out. Let's clear out that equation. Okay, we have another fraction, so we want to do the entire top. So put it in parentheses, divided by the entire bottom. So we have x to the third plus 5x squared plus 6x. And let's check it out. Really weird graph. Okay, so I'm going to zoom in. We have a bunch of stuff happening right in here. I don't really need all this stuff on the left and on the right. So I'm going to change my window a little bit just to make sure I can see it a little bit better. Instead of going for those -10s and 10s, maybe we'll go into the -5s and 5s just to zoom in a little bit. Alright, so that's a little bit better. Let's check out these three x values. So we're going to focus on -3, which, since I'm counting by ones, is right here. And notice how we can imagine drawing in that dotted line, okay, in our graph. So that would be a vertical asymptote, okay, that remove or non-removable infinite discontinuity. So we'll label this as a vertical asymptote. Now if we take a look at -2, which is right here, we kind of have the same thing happening. Okay, we have that dotted line we can imagine drawing in our graph, and it's going to separate these two pieces. So here is another vertical asymptote. And even if we check out 0, okay, we have this piece that's going down, but over here this piece is continuing up. We have that another division, another asymptote right there happening on our graph. So actually all three of these pieces would be vertical asymptotes. Alright, so if we check out this next one, we actually did not do this one just yet, but let's actually try to figure out what the domain is and see if we have any x values that do not work. Okay, so since we have a fraction, we know that the bottom cannot equal 0, so let's first set up that. But then we have this square root part that we know the radicand, the inside quantity, has to be greater than or equal to 0. So let's solve each piece separately. Now over here, this is a true statement. Okay, so we're not really getting any restrictions on our variable from the fact that our denominator is 4. Okay, so we don't have any x's in here. We don't really have to worry about anything. This is a true statement, so no worries over here. But as we start to solve over on this side, we can subtract 4 over. And when we divide by -1, we got to switch that sign, which means we're going to end up with a +4 over here. Alright, so this is our domain, but now we want to see, are there any points of discontinuity? Well, we don't have to worry about anything here. And this is telling us every single x value is going to work as long as it's less than or equal to 4. So if we check out a graph, let's do the whole top, which is the square root of 4 minus x, and we're going to divide it by 4. And there's our graph. Alright, so notice, take a look at our picture, and we said that every single x value is going to work as long as it's less than or equal to 4. So if we think about the graphically speaking, it can go as far left as it wants because we have this little arrow, assuming there's a little arrow there on our graph. And as we continue to go across our graph, it stops here at +4, which is our ending point. But notice how we don't really have any asymptotes in our graph, okay? It is completely continuous on its domain. You can actually draw this picture without having to lift up your pencil. So since we have a true statement over here, we don't really have any of those asymptotes, any of those values for x that do not work, we would say that this graph is continuous on its domain. and we actually found its domain, okay, all the x values that are less than or equal to 4 are going to work. So since we did not get anything like x cannot equal something, okay, we did not get anything like that, it's telling us that it is continuous. Every single x value is going to work as long as that it's less than or equal to 4. Alright, so this time, instead of focusing on those vertical asymptotes, okay, those non-removable infinite discontinuities, we're going to focus on the removable discontinuities, which were those holes, okay? So something's going to go on just a little bit different in here. And notice how if we tried to start out to figure out our domain, since we're dealing with a fraction, we know the bottom cannot equal 0. So let's first figure out the numbers that cannot work. If we have x plus 3 cannot equal 0, and then x minus 2 cannot equal 0, a restriction on our x in this case is that it cannot equal negative 3, and a restriction in this case is that x cannot equal 2. Okay, so our overall domain, our restrictions that we have, is x cannot equal negative 3 and it cannot equal 2. But we want to try to figure out what type of discontinuity is happening at these 2 points. Are we going to have an asymptote or are we going to have a hole? So if we look at this a little further, okay, something interesting is going on here. Notice how there is a piece of our denominator that matches a piece of our, a piece of our numerator that matches a piece of our denominator. Since these two items, these factors, are exactly alike, we are able to cancel them out because we're doing this division. So what we're actually left with up top would be just a factor of 1, because the entire top is gone. We need a factor of 1 left. And the denominator is just x minus 2. So in this particular case, our original fraction was able to be simplified. Okay, we can actually remove, okay, keyword there, remove a piece of our graph. Okay, so let's just hypothesize something here. Since we were able to remove, okay, or cancel out the x plus 3, this solution, or x value that does not work, came from that particular factor. So since we are removing it, that would in a sense make it a hole. So we're going to hypothesize here and say that at this particular value of negative 3, since we were able to remove that factor, there is going to be a hole on our graph. Now this piece, notice how we still have that x minus 2 left over, which is where this domain restriction came from. Since this one is left over, okay, we're going to hypothesize that it is a vertical asymptote. Since we were not able to remove it, that would mean it is a non-removable discontinuity. It's probably going to be a vertical asymptote. So let's just check it graphically and see if our hypothesis is correct. Maybe turning it on might help. Okay, so we want the entire top, which was x plus 3, and we're going to divide it by the entire bottom. Now, I'm going to have to put the entire bottom in parentheses, meaning parenthesis here as well as here. So we're going to have a double parenthesis at the beginning and a double parenthesis towards the end. So there's my first parenthesis, and then I need an x plus 3, and then an x minus 2, and my last parenthesis to close it off. So there's my double parenthesis. So if we were to graph it, let's take a look at what's happening here. Alright, so look at this. We said we have 2 values that are not going to work. We have that negative 3 value where there's going to be a hole, and then this 2 value where we have that vertical asymptote. Well, if we first just take a look at the 2, which is right here, notice how that's where we can think about drawing in a vertical line. Okay, so that's where our vertical asymptote is coming from. So far, we know that at this discontinuity of 2, there's going to be that vertical asymptote. But the hole is a little bit trickier because over here at negative 3, it actually looks like we have a point there. Okay, our graph is continuing, but it looks like there's a point. This is where we got to be careful, because if we were to actually put in 3, okay, if we were to use that I don't want to use second. If we were to hit the trace button and actually select an x value of -3, I know it looks like we have a point there, but notice how when we select it, it does not have a y value. So there's actually a hole there, okay? There's no point, there's no y value at that particular location. So what's weird about your calculator is that your graph is getting as close as it can possibly get to that value of -3, but there's nothing there. And it's so close to that value that it actually looks like, there is a value. So you can check to see if there's a hole by selecting that value when you hit that trace option. So notice how if I were to trace maybe -3.00 or 0.00001, I actually have a y value. So there's a point there. And if I actually select -2.99999, I actually get a point there as well. But the moment I select -3, I do not have a point. So there's that hole in the graph. We would actually denote it with that little open circle. So our hypothesis was correct. Since we were able to literally remove or cancel out that factor, that's where the hole is coming from. That's why it's called a removable discontinuity. You're removing that piece from your equation. But since this one was not removed, it's still left over. Okay, that is meaning it's a non-removable discontinuity, so that's where our vertical asymptote would occur. Alright, so let's try the next one. Again, this little thinker guy means that you can pause the video and try it on your own if you want to, but I'm going to go ahead and do this one with you guys as well, so that this lesson isn't as long as I would like it to be. So when we take a look at this one, let's first find our restrictions. What is our domain? We're dealing with a fraction, so we know our denominator cannot equal 0. And in this case, since we have an x squared going on, to figure out what our x values that do not work, we might want to factor, again, in this case. But this one's a little tricky because it's not following that I am format. It's actually starting with a number of 2 instead of the number 1. So we want to multiply this a and c value, which if we were to do that, we would get -14. And we want to try to figure out what can multiply to -14 but add to a -13. So let's think about that for a second. Two numbers that can multiply to -14 but add to -13 would be -14 and a +1. But again, since this did not begin with a 1, we need to bring this number 2 into play. We're going to divide both of our numbers by 2. And this one actually simplifies to -7, whereas this 1/2 does not, so we can move the 2 out front. Alright, so if we think about our two factors, either x minus 7 cannot equal 0, or 2x plus 1 cannot equal 0. A restriction on our domain from our first factor would be that x cannot equal 7 when we add it over. And if we do a little bit of solving here, a restriction on our second factor would be -1/2. So every single x value you can think of would work in this particular problem, but x cannot equal -1/2 or a +7. Alright, so we want to figure out what are these discontinuous values. Okay, if x cannot equal these numbers, that means there's a discontinuity. Is one of them a hole? Is one of them a vertical asymptote? Are they both holes? Are they both vertical asymptotes? What's going on? Okay, so let's, I'm going to erase factor up here for a second. And I'm just going to continue writing our equation for us to notice something. Okay, so this denominator, we were actually able to factor as an x minus 7, so I'm looking right here, and a 2x plus 1. Okay, that's how we can change the denominator. But notice how a piece of our numerator, okay, actually our whole numerator, matches a piece from our denominator. These two factors are exactly the same. So since we're dividing, we are able to remove or cancel those out. So all we're left with is a 1 over x minus 7. So let's hypothesize what's going on down here. Since we were able to remove this particular factor, the x value that does not work that came from that factor is a removable discontinuity, meaning that it's a whole. And the x value that came from this particular factor was the x cannot equal -1/2. So this particular, at this x value, we're going to have a whole because we were able to remove that factor. But since the x minus 7 was not removed, it's a non-removable discontinuity. This is where our vertical asymptote is going to be. Or at least that's what we think of so far. So let's actually graph it to check it out. Alright, so we're going to clear that out. The whole top in parentheses, 2x plus 1, divided by the denominator, 2x squared, minus 13x minus 7. Alright, now before I hit graph, I'm going to change my window because I'm only dealing with 5s, but notice how I want to go all the way over to a 7. So I'm going to, maybe I'll change my x value. I'll keep that at 5, but I'm going to go all the way over to 10, just so I can see that x value of 7. Alright, there we go. Okay, so we have right here at the value of 7 on our x-axis, we thought that there'd be a vertical asymptote, and notice how at 1, 2, 3, 4, 5, 6, 7, we can think about drawing in that dotted line. Okay, so that makes sense. We have a non-removable vertical asymptote right there at 7. Okay, so this number is a discontinuous point. But at -1/2, we thought that there would be a hole, and notice how it kind of looks like there's a point there, but we can check it by actually tracing a value to that point. So if we actually select -0.5 or -1/2, and we hit enter, look at how it's not giving us a point, which means that there's a hole there. I know it doesn't look like it, but there is an actual hole at that value of -5. So our two x values that we found that did not work, we were able to label them correctly as either a hole or a vertical asymptote. So you can always check your work by using your calculator, but notice how just hypothesizing what's going on here, we were able to assume the discontinuities correctly. We were able to remove that factor, which means that we have a hole, but since we could not remove that x minus 7, it's still there, we have that vertical asymptote. Alright, last but not least, we're almost done. Okay, hang in there. I know this is pretty long, but this is our last one. We're going to try to figure out what is the domain, and do we have any discontinuous points? Can we label them as holes or vertical asymptotes? If we take a look at our equation, we only have a fraction going on, so we know that the denominator cannot equal a 0. But notice how, since we don't have an x value, and we take a look at our statement, it's actually true. Okay, so we can't really find an x value that does not work, meaning that we don't have, okay, there are no discontinuities. Discontinuities. There we go. Alright, so we can't really find anything, meaning that every single number is going to work. So we would say, since every single number is going to work, it is continuous on its domain. And since every single number is going to work, its actual domain would be all real numbers. We can't really find an x value that's not going to work. Now this one's going to be able to be simplified just like the other ones. Okay, we can cancel out those 3's to just, or excuse me, to just get a value of x, but we don't really have any restrictions. Okay, there are no discontinuities, there's no restrictions on our variable, so our domain is continuous, particularly on this all real number domain. So good luck on the practice, good luck on the mastery check most of all, and that application section. The application problems are going to be a little bit more difficult, so please check out the walkthrough video to help you with those. I know this section was a little bit longer than I wanted it to be, but thanks for being a good sport about it and watching the whole thing. This can be one of the more difficult sections, so if you do need help, please don't be afraid to ask for it, or even go back and watch a few different sections or pieces of this clip to help you out, alright? So I'll see you guys next class.